Welcome to lecture 17 of Financial Econometrics, and this lecture would focus on the assumption of homoskedasticity or the issue of heteroskedasticity. Moving towards the contents, before I discuss the contents, let me give you the background on this topic. We have discussed that there are certain assumptions that need to be fulfilled before we can apply the technique of ordinary least square, the OLS technique. And one of those assumptions is homoskedasticity. We want that the data should be homoskedastic. The error term should be homoskedastic. That is, the variance of the error term should be constant, and you can go back to the assumptions of regression lecture and review the discussion over there, because we are not going to repeat that discussion. We are going to build our concept on the basis of that lecture. So once that assumption of homoskedasticity is violated, then we have an issue of heteroskedasticity. So we are going to discuss what are the consequences of heteroskedasticity. What are the consequences? What would happen if the error terms are not homoskedastic? If the variance of the error term is not constant, then what would happen? What issue would it raise? How would we detect that there is heteroskedasticity, and then what remedies can we take? So starting with the basic idea, although we have discussed, but let me give you a quick idea. Homo mean equal and skedasticity mean spread or variance. So when we say homoskedasticity, we mean that the variance or the spread in the error term is equal, right? So that's what homo means. And when we say heteroskedasticity, that means that the variance or the spread is not equal. It varies, right? Or we can say hetero means more than one, and skedasticity means spread or variance. Then that would mean that there are more than one variances. So symbolically, when we have homoskedasticity, then we would say expected value of error term would be equal to sigma square. The sigma stands for the variance. Sigma square stands for the variance. And if heteroskedasticity is represented symbolically as sigma I square. So the difference is in subscript. When we have homoskedasticity, then we do not have the subscript, and when we have heteroskedasticity, then we have a subscript of I. And what does this subscript mean? Is that for that the error term is different across observation in the sample. So for each observation, this I represents the observation. For each observation, we have a different variance. So when we have equal variance for each observation, the same variance for each observation, then that would be symbolically represented by this. Anyhow, and normally this heteroskedasticity issue is related to cross-sectional data. If we look at this chart, we have the independent variable. It is a three-dimensional chart, so you can see the density over here. And we have saving as dependent variable. You can see that the spread between the error term is equal no matter at what level of income we are. At all level of x variables, the spread is equal. So this would be called homoskedasticity. As opposed to this, if you look at this, the same graph, but now we can see that the spread is lower over here at this x value, at this level of income. When income is lower, the spread is lower. The saving, this is the level of saving. So some people would save less, some would save more, but as compared to other level of incomes, the amount of saming is somewhat similar among the cross sections. As we move towards the higher income levels, we can see that the spread in saving increases. Some people save more, some people save less as compared to previous income levels, and that is because once we have more discretionary income, then some people might want to spend them on some luxury item and other might want to save them. So they have the choice to save higher, but in this case the choice is somewhat restricted. Without going through the theoretical aspect of this relationship, what we are interested is understanding what heteroskedasticity is, and it is that at this level of x, the variance is different as compared to this level of x or this level of x. So when this happens, then we say we have a problem of heteroskedasticity. And what would happen? What are the consequences when we have heteroskedasticity? One thing, we know what blue is. Blue stands for best linear unbiased estimator. We have already discussed again this somewhere in the end of assumption lectures. So when we have heteroskedasticity, although our estimators are unbiased, right? What do we mean by unbiased? Is that if the population's coefficient is this, beta 1, then the coefficient that we would have from a regression, even if there is heteroskedasticity, we would have the same beta value. The expected value of beta would be same, the expected value of coefficient would be same, so it is unbiased, but it would not be efficient. That is, let's say compare this one, this distribution of beta as compared to this one. So the second distribution, we have a higher variance, it is not more efficient. So we say that although it is unbiased, but it is not efficient because the variance is higher as compared to this one, the variance is less. So when we have heteroskedasticity, the variance of this beta, estimated beta, would increase. So if the variance increases, the standard error would increase. And one thing we might have discussed in our previous lecture is that how do we measure this t value, because the significance, the acceptance or rejection of the hypothesis is decided on the basis of this t value. So if how do we measure this t? This is the coefficient value divided by the standard error. So this 21 is coming from 8.81 divided by 0.40. Now, although if there is heteroskedasticity, then we do not have an issue with this value. This value still would be good. So the estimates are unbiased, but the issue would happen is that this standard error would increase. And if this standard error would increase, that is, the denominator of this t formula would increase. If the denominator increases, the t value would decrease. So instead of getting a 21, we might get, say, 0.21, right? If it increases a lot, the standard error increases a lot. And if this t value, the interpretation of this t value, if it is greater than 1.96, then we say, 1.96, then we say that the coefficient is significant, the variable is significant, right? We have enough evidences of rejecting the null hypothesis and accepting the alternate hypothesis. But if this t value decreases, so we can draw inference, right? So if this t value decreases, it is lesser than 1.96, then although we do have the estimate, but this estimate, we cannot draw any statistical inference from this estimate, right? So what would happen is, in case of heteroskedasticity, is that the standard error would increase, and when standard error increases, the t value would decrease, the p value would increase, the confidence interval would be higher, and all these things, the t value, the p value, and the confidence interval, are related to the drawing the inference from the regression. So the issue is that we won't be able to draw the inference, right? So what are the reasons, some of the reasons that would generate heteroskedasticity? One is the error learning model. And what this means is that there are certain cases where the heteroskedasticity is inbuilt in the population, let's just say. What does this mean is, consider a car driver, right? So if we draw this graph of the effect of number of years of driving, right, experience, and its effect on, say, accidents, or say rather error in making, during driving, what would happen is that as experience would increase, the errors would decrease, right? So if we input some kind of a model where this situation would happen, then you would see that the spread would decrease with the increase in experience. With lower experience, there would be higher errors, there would be higher chance of making an error. So as experience increases, the spread of the error would decrease, there would be lesser errors. So this issue is inbuilt in the model. So we can call it that this is the population heteroskedasticity. Second issue can be due to outliers. Outliers are the extreme values in the data. So if there are outliers, then there is a chance that due to those outliers, the spread of the error would be higher. And if that happens, then we would have the issue of heteroskedasticity. So second reason could be outliers in the data. Third could be omitted variable biasness. Now, what do we mean by omitted variable biasness? Although we would have a specific chapter on this one, but let me give you an idea. When there is a variable that theoretically should be there in the model, it is an important variable. Let's say we are studying the effect of income. Let's say we are trying to understand the factors of consumption. So one of the factor of consumption is income. The higher the income, the higher will be the consumption. But there is another factor, which is wealth. I mean, some people would have lower income, but they would have higher wealth. They might have inherited that wealth from their say predecessors. So there is an important factor of wealth. If we omitted that wealth variable, then what would happen is that we might see that there is a heteroskedasticity issue in that model. And that heteroskedasticity issue had been is due to the issue of omitted variable. And if we input that variable back into the model, then we might see that this heteroskedasticity issue might disappear. So one of the reasons of heteroskedasticity might be omitted variable. One another reason can be functional form, and it is related to omitted variable. Let's just say in our previous lecture, we somewhere discussed that income is the function of age. So if we draw a linear relationship, then that means as age increases, the income would increase. But you would know, and we have already discussed its reasons in our lecture of functional forms. We say that the relationship between age and income is somewhat non-linear, some kind of a parabolic relationship. As age increases, the income would increase, but to some point, and after that, let's just say after retirement, the income would start decreasing. Now, if we capture this relationship based on a linear model, then what would happen is that at this point, the error would be lower. They would start increasing, then they would decrease at this point, and after this point, they would again start increasing. So you can get an idea that If the functional form is not correct, functional form is misspecified, then we might also see the issue of heteroskedasticity. So we just need to correct the functional form. So instead of regressing the y variable on age, we need to include, let's just say, age square in the equation, and then the functional form would be corrected and our heteroskedasticity issue might be resolved. So one more reason is skewness. If we know that skewness is when the data is non-normal. I mean, either the graph is shifted towards skewed towards right hand side, or it is skewed towards the left hand side. In either cases, we might see the issue of heteroskedasticity. Just to give you a graphical idea, it is not necessary that heteroskedasticity might look in some specific way. It can be increasing. The error might increase as the x increases. They can. I mean, this is where the error is constant. In all other cases, the error we see the heteroskedasticity issue in error. And the point is that how do we test? How do we find out whether there is heteroskedasticity or not? So we have covered the question of what heteroskedasticity is. Then we discussed what are the consequences of heteroskedasticity. And now we are on our third question, which is how do we measure it? How do we know that there is heteroskedasticity? Once we measure it, then we would see how do we resolve it. So one method is, the basic method is graphical method. We can draw some kind of residual plot, and what residual plot is, we plot the error term, the residual with x or y variable. So in this case, all these are residual plots, and these residual plots can give us a pretty good idea whether there is heteroskedasticity or not. But normally in extreme cases, we would be able to identify heteroskedasticity from these graphical methods, and then again they are not statistical tests. So these all graph shows heteroskedasticity except for this one where the error term are constant. So irrespective of the value of y or the x variable, the error term are same. This graphical method is also called informal method. We can move towards the formal testing. We can have different tests. We can have Park test, Gletscher's test, we have Goldfield test, then we have Bruce-Pagan test, and you can see when they were invented. And then we have White test. Now, most of the time, we do not use these tests. These are used because these are more robust. They are latest ones, and so I'm not going to give you theoretical idea of all these tests. We are just going to discuss these two theoretical method or steps of these tests, because we apply these tests using statistical packages. So what we are going to do is we are going to apply them in those statistical packages and see how things happen. But just to give you an idea, what Park test is, what it does is, it first runs the OLS regression. So simple OLS regression, let's say we have dependent variable and we have an independent variable, alpha plus beta x1. We run this regression, we get its residual. How do we get the residual? Y hat minus y bar, the original value, observed value, minus the estimated value. Once we have the residual, we take the square of those residual and then take the natural log of this squared residual. Then what do? Is we run the regression of log residual, which we got from our second step, so from previous step, on the log of independent variables. So our new model would become this, rather I would write it like this: natural log of the residual, the error term, is equal to natural log of, this would also be ln, our independent variable, right? We again run the OLS regression using this model, this functional form. This is, if you remember, it is a log functional form. And the null hypothesis of this this test is homoskedasticity, and the alternate is obviously heteroskedasticity. So we check the p-value of this coefficient. If the p-value is less than 0.05, that means we reject the null hypothesis and we accept the alternate hypothesis, which is heteroskedasticity. So the idea is, if p-value of this second regression, this auxiliary regression, is less than 0.05, then we have the issue of heteroskedasticity. Right? So PAR test is nothing but we have a main regression, and then we have some functional form. We convert the values using some functional form, and then we have an auxiliary regression and we test it. Similarly, Lister test is different in one aspect. Rather than taking the log of squared residual, what we do is we use the absolute error term in our auxiliary regression. So instead of taking ln of error term, what we do is we take absolute error term, that is negative value would be converted into positive, and regress on independent variable but not on the log of independent variable. So again it would be so the equation would look like this: alpha plus beta x1. So instead of taking log on both the sides, we take absolute value of the error term and we do not take the log. And again the idea is similar. If p-value is less than 0.05, then it means that we have the issue of heteroskedasticity. Now all the other tests, whether it is Brush-Pagan or white text, except for the Goldstone test, in Goldstone test we do some kind of dividing the sample, and then it is a technique you can study in book. So in Brush-Pagan test and white test, we also do a similar kind of main regression and then auxiliary regression. But there we do some other kind of transformation rather than log or absolute error term. So we would move towards the remedies. First remedy is the easiest one, is to use white standard error. I mean, again, before we discuss these remedies, we previously saw that there were some cases where we omitted a variable and that generated heteroskedasticity. We omitted and we had an outlier issue that generated heteroskedasticity, or we had a misspecification functional form, misspecified functional form that generated heteroskedasticity, or there was a heteroskedasticity in the population. In all those cases, we need to correct the issue. I mean, if there is omitted variable biasness, we need to correct the omitted variable biasness. If there is a misspecified functional form, then we need to correct the functional form. If there is an outlier, we need to treat the outlier. So the idea is that all these remedies should be performed after correcting these issues, after correcting the issue of outlier, misspecified functional form, right? So the remedies we have is white standard error or new west standard error. Then we have respecify variable or model, and then we have weighted least square. So starting with white standard error, it is the most easiest one. It is called robust standard error. By the way, what this white standard error would do is, again, we do not need to understand the formula or the method because we are going to see this in applied form in the software. What we are going to do is there would be an option while we are running the OLS regression of robust standard error. We are just going to take that option and it would give us robust standard error. But the idea is that the issue was, when we are discussing heteroskedasticity, the issue was with standard error. We knew that standard error was somewhat higher. So we need to correct these standard errors. So instead of using the the original formula of standard error, we are going to use some modified formula of standard error. So those techniques that are used in your statistical package would use some kind of a modified formula of finding the standard error. So this is what we call robust standard error. So it would correct the issue of heteroskedasticity and the standard error. What it would do is it would recalculate standard error using an adjusted formula. That is what just I said, that we would have standard errors, but those standard error would be calculated using a modified formula. The second method is to respecify. So if we can scale the variable, sometimes a particular size variable causes problem. So what do we do is, instead of taking GDP, we can scale it over the population. So we get per GDP, per capita GDP. Or normally you would have seen in finance that that some variable is divided by total assets, right, or number of employees. So that is done, that is called scaling the variable. Especially if you have studied the earning management models, then you would see that they use this divided by total assets, and that is because they scale the variables, they standardize the variables based on total assets, and that also removes the heteroskedasticity issue. We can go for log-log model. That is, we change the specification of the model. So this brings us to the end of the theoretical discussion of heteroskedasticity. Once we cover the issue of multicollinearity and the autocorrelation, then what we are going to do is we are going to move towards our statistical package, and we would see that how do we solve or identify, run the tests in our statistical package, which is Stata.